Hello and welcome to Mechlin 360. All right, so in this video, I want to solve a question with you to illustrate the concept of the average normal stress. Okay, so this question is about okay, let's read it together. A couple moment, or let's say a couple M of magnitude 1500 Newton. So that is the couple is applied to the crank of an engine. Okay, so if you don't know an engine, this is actually what we call the piston cylinder arrangement. So what happens is that there is this sort of force which is applied to the cylinder. Okay, this is called the connecting rod, and then this is called the crank. So think about it this way: as the load is acting on the cylinder will be doing something like this. So up, down, and as it goes up and down, this crank will be doing this. So it will be rotating in that sense. So as this load is applied, it causes the crank to be rotating. All right. So that's the basics about internal combustion engines, or let's say engines. Okay. But let's focus on the statics behind this. So we want to draw a free body diagram. Okay. So now if you draw a free body diagram, this is what you are going to see. We have a cylinder here. Okay. And the load is coming like this. Then there is this connecting rod which connects it this way. And then we have the crank which is connected to the connecting rod this way. Okay. Now this this connection here at A is some sort of a pin, because if there is no pin here, then it means the A can also move just anyhow. But then there is a pivot so that this AB will rotate about A. So A can be thought of as a pin with reaction AX and then AY. Okay. So this is the free body diagram. We need to introduce the couple moment M. Okay. As well as the dimensions. So this is 80 mm, and the distance from the cylinder all the way to B is given by 200 mm. All right. So how can I solve this problem? All right. So then, okay. So let's sum moment so that we can get, okay. By the way, because the cylinder is inside this, there is going to be some reaction coming from the wall to the cylinder. Okay. So we can, okay, so we will get this actually. Okay. So if we want to find the forces, we would have to use our equilibrium to find it. But then from the question, we're asked to determine the force P required to hold the engine system in equilibrium, and then the average normal stress in the connecting rod BC, which has a 450 millimeter squared uniform cross section. All right. So let's first of all solve for R. Okay. Or any way you want to do it, we will still solve it. So let's sum moment about point A. If we sum moment about point A, it will eliminate A. So summing moment about point A to 0, then we have H, and this this R here is having a distance all the way 200 plus 80, so it's going to be R multiplied by 280, which is 0.280 meters. And then okay, this R will go this way. It's going to create a moment. So here it's supposed to be negated because we are assuming that clockwise is positive. All right. If you do this, don't forget that there is also P here. But what's the moment of P? So the moment of P is actually 0. Why is the moment of P 0? Because the line of action of P will pass through A. This is interesting. So in other words, P does not cause a moment. All right. So it is 0. Okay. Now, there is a couple moment, which is what? So let's go back. The couple moment has a magnitude 1500. So it's going to be clockwise. 1500 should be equal to 0. So that R will be 1500 divided by 0.280. And what is that? So we have 1500 divided by 0.280. Then we are going to get 5,337. So 5.3, so 5,357. So 5.36 kilonewton. So that is the R for you. Okay. But the question said we should find P. Okay. So the next step, or the next thing to do, is to use okay. So we know this R. So we can now use the free body diagram of just the cylinder. Okay. Now, if I am to look at only the forces acting on the cylinder, then I have this force, I have the cylinder, then there is this force P, and there is going to be R, which is acting on it. And then there is going to be some sort of force FBC coming from the connecting rod, this one. Okay. So this free body diagram is actually looking at just the cylinder. But now I know R, so I can say that this one is 5.36 kilonewton. Okay. So again, I will use equilibrium to solve for FBC. Okay. Now to get FBC, or okay, let me do it this way. So I want us to solve this. Look at this. If FBC is acting on this line, now we have 200 coming down, that is the length here, and the distance is 60. So 60 and 200. So what will be the length of the hypotenuse? So you have something like this. Here is 200, here is 60. So what is this? So the hypotenuse is nothing but the square root of 60 squared plus 200 squared. And what is that? Okay, so that is 208.806. 208.806. So what you will do is that basically, if this system is in equilibrium, then summation of forces will be 0. Okay. So summation of forces along the x will be 0. So we will resolve FBC along the x. And then to resolve FBC along the x, okay, so we are going to use this triangle. FBC will be acting along this line, which is the connecting rod. So the y component will come down here, and the x component will come the other way. All right. So what this means is that we are going to get the x component of FBC as 60. Okay, so minus 60 divided by the hypotenuse, which is 208.806, and then okay, multiply by FBC. So in fact, this is the x component of FBC, and then minus 5.36, because that is also coming this way to be 0. Let's solve for FBC, and that's going to give us 5.36 times 10 to the power 3, which is kilonewton, divided by 60, and then multiply by, okay, there is a negative sign here, so the whole of this is going to be negative. So multiply by 208.806. Therefore, FBC is going to give us, let's pick our calculators and do it together. So 5.36 times 10 to the power 3 divided by 60 multiplied by 208.806. Okay, so FBC is actually 18, so minus 18.65 kilo newtons. And this force is actually a compressive force. Sorry, it's a compressive force. That is why it is negative. So compressive. All right. So let's sum forces along the y to be 0. What do we have? We have the component of so minus p, because p is coming down, and then the component of FBC along the y direction. So that is going to be 200. So minus 200 divided by the hypotenuse, then I'll multiply it by the force. Should be equal to what? 0. Okay. But then now you know. So P is going to be minus 200 multiplied by 208.806. And then you multiply this by FBC, which is minus 18.65. So P is nothing but minus 200 divided by 208.806 multiplied by minus 18.65. And what is that? This will give us 17.86 kilonewton. And that is actually the P which is required for equilibrium. Okay, so the question, the first part has been solved. Now he said we should calculate the average normal stress. So the average normal stress will be the load. Oh, sorry. He said the average normal stress in the connecting rod BC. So we are going to use the load on the BC, which is the FBC divided by the cross-sectional area. So the compressive stress will be minus 18.65, which is the load FBC, times 10 to the power 3 kilonewtons. And then the cross-sectional area is what? 450 millimeter square. So yeah, so that is it. Therefore the average stress is going to be minus 18.65 10 raised to the power 3 divided by 450, and then I'll get minus 41.4 megapascal, and this is actually a compressive stress. All right, so the problem has been solved. Thank you very much for watching.